Two pieces of homework that we had last night. First one was practice question set number 10. Only 3 questions on this. Let's take a look at it now. Starting with multiple choice question number 1. We got 3 charges in a row here, X, Y, and Z. We kind of know the charges of them. It says minus 3Q, plus 3Q, and minus 3Q. I had a couple of people ask me what Q means. Is it coulombs? No, it's not coulombs. So what does it mean? I don't know. Hey, all it means is that I guess that we have the same charge for X, Y, and Z. That's really all we know. We have the same charge for X, Y, and Z. Okay, whatever that charge is. We do know the distance specifically is 2 meters between X and Y, and the distance between X and Z is 4 meters. We want to find the magnitude of the net force on X. Well, listen, we don't know what the charges are, but there's no reason to tackle this question, at least initially, any different than we tackled all the rest of those questions with 3 charges in a row. We draw a Freebody diagram. That's what we do. Now, we are clearly going to have to end up doing something else here because it's not quite the same as those questions, but it starts off the same. So let's draw that Freebody diagram now. Let's pretend Y isn't there. Okay, Y is non-existent. If we look at X and Z, we know that that's an attractive force because we got a negative and a positive. If it's an attractive force, X is going to go which way as a result of that force? X is going to go left or right, Silveros? It's going to go to the left as a result of that force. I'm going to call this the force of Z on X. You can call it just Fz if you want. Call it F1. I don't care what you call it, as long as you recognize that it's the force of the first one on the second one. Now, X and Y are opposite charges as well. One's positive, one's negative. That means X will be attracted towards Y. The force of Y on X is going to go this way, to the right. Now, we know what the value of Fyx is. They tell me that the force of Y on X is 6 newtons. So I'm going to fill that in. All right. Now, if we can find the value of Fzx, then all we're going to have to do is add these 2 forces together, one being negative, one being positive, in order to get the net force, right? Now, there's a couple ways that I could think of to get the force of Z on X here. Can anybody think of one way to get the force of Z on X? Some of you guys must have got this question right? Zach, what'd you do? Six by 16, okay, which would have been R squared. Okay, I see what you mean. So 4 squared is 16, and then you multiply that by 6, okay. Yeah. Oh, interesting. That's interesting, actually. And that gives you 24, right? Yeah, it's interesting, actually. Yeah. So Fzx would be 24 newtons. Okay, that's interesting. I never thought of that way. Okay, all right, there's 3 ways then of solving for Fzx. That's a good way. Okay. Although you have to be a little careful with that because that's fairly specific to this question here. But having said that, that's fine. If you can think of that in your head, that's absolutely fine. Anybody think of another way? This actually is kind of like one of the ways that I was going to do, but mine's a little bit more structured and a little less thought to my way, and a little bit more structure. The way that I actually did it was variable value changing. I said the value of Fyx is kq1 q2 over r squared, and I said that's equal to 6.0 newtons. And then I said Fzx is equal to k times, well, the charges are the same, right? We're not talking about new charges here, but we're talking about the same charges. We're not upping the charges or decreasing the charges, but we are changing the distance that separates them. For Fyx, the distance was 4 meters. Now for Fzx, the distance is 2 meters. So I'm going to say that the distance is now 1/2 of what it was. Does that make sense? It was R, now it's 1/2 R. It was 4, now it's 2. So let's pull that number out front. We got kq1 q2 over 1/4 r squared, which is the same as 4 kq1 q2 over r squared. Well, we know what this value is. It's 6 newtons. So 4 times 6 is 24 newtons. And we get exactly what Zach got there. Now, that's not the answer. The 24 newtons isn't my final answer. Remember that's the force of Z on X. What's the final answer here? If we got 24 newtons to the left and 6 newtons to the right, the final answer is 18 newtons to the left. So my answer would be C. Anybody do it even differently than that? Not a variable value changing thing at all. Yeah. Solve for a Q, you mean? Okay, solve for the value of Q. Yeah, that's the other way to do it. You can say that the force of Y on X is 6 newtons, and it's also equal to K, well, we know what K is, times Q1 times Q2, but Q1 and Q2 are the same value, right? So that becomes the same as Q squared over 4 squared. So if we know this, we know this, we know this, we can solve for Q, and then, well, we know that charge Z is the same value, and then we can just say F is equal to K QZ QX over 2 squared, and we'll get 24 newtons there as well. Does that make sense? Hey, how many people did it? How many people did it my way? Hey, how many people did it this way? Maybe about half and half. All right, good. They're both good ways. All right, next question. 3 charges, Q1, Q2, and Q3 are placed at the vertices of a right angle triangle shown below. It looks like one of those 2D force problems here. We want to find the magnitude of the net force on Q2, and we want to find the angle labeled there as well. All right. Somebody asked me yesterday, I think, about expressing the direction for something like this. Was that this class? And I said, we can't really express this as a north, south, east, west thing because that's not our frame of reference. Remember I said, listen, if you get a question like that on a test, you're probably just going to have to label an angle, basically, that is given to you in a diagram. That's exactly what we've got right here, right? We have to just label the angle or calculate the angle that's labeled in the diagram that's given to us already. So basically what we got to do here is find the net force, magnitude, and direction for the next 2 questions. All right. Let's draw a Freebody diagram here. We've got Q1 and Q2 are both positively charged. That means the force of 1 on 2 is to the right. Q3 and Q2 are both positively charged, so the force of Q3 on Q2 is upwards. We're going to have both of those forces, repulsive forces, therefore it's to the right and up. Listen, we didn't even really need to figure that out because they kind of give it away to me already, right? Because they draw the resultant vector up and to the right, then we knew the force must be up and to the right. Anyways, let's calculate the value of F12. It's K Q1 Q2 over R squared. It's 8.99 times 10 to the 9 times Q1, which is 4 times 10 to the minus 5. Be careful about the exponent there. Times 4 times 10 to the minus 5, because that's what Q2 is as well, divided by the distance, which is 0.500, and we got to square that. Does anybody have the value of F12 there? All right, let's pull out the calculator there and solve it. We've got 8.99 times 10 to the 9 times 4 times 10 to the minus 5 times 4 times 10 to the minus 5 divided by 0.5 squared. Gives us a value of 57.536 newtons. Now let's get the value of F32. It's 8.99 times 10 to the 9 times 3 times 10 to the negative 5 times 4 times 10 to the negative 5 divided by 0.200 squared. And the value for this is going to be, let's see here, 8.99 times 10 to the 9 times 3 times 10 to the negative 5 times 4 times 10 to the negative 5. And we divide that by 0.2 squared, 269.7 newtons. Is that right? Both of those right? All right, so now we got to combine these here to find the resultant vector, magnitude, and direction. We've got 57 And we've got 269. And our resultant vector goes right here. What do we get for the value of the force there? You 276 newtons is the hypotenuse. A squared plus B squared equals C squared. And then the angle is going to work out to be 78 degrees, 78.0. Okay, this is one that we don't often see. This is not to be expressed in scientific notation, right? This is just standard notation. How do you know it's standard notation? Because they don't tell you it's standard notation. Well, they don't tell you it's scientific notation. In the absence of telling you to put it in scientific notation, then leave it in standard notation, okay? So it is 78.0. We want to record our answer to 3 digits, so we need not just 78, but 78.0, and we'd express that as just simply 78.0. Don't drop the decimal point. Okay? If it was b times 10 to the w, we would say, sorry, scientific notation, b times 10 to the w, we'd say 7.80. If it was a decimal bc times 10 to the d, it would be 7801, because the exponent would be 1. Honestly, I wouldn't expect an angle to be a scientific notation thing. It's probably always going to be a standard notation thing. All right, quiz tomorrow on exactly this stuff. I think you'll find actually that the quiz tomorrow is probably a little bit easier than what you did here. Specifically question number 1. It will be one of those questions where you've got 3 charges in a row. But I think you're going to find it's a little bit easier than the question that we had here in our practice question set. All right, we had a little bit more homework as well. And the other homework we had was page 538, number 4 to 10. All right, let's take a look at 7b, question 9, and question 10. All right, question number 7 says 2 identical conducting spheres have charges of 5 times 10 to the minus 5 and 6 times 10 to the minus 5. They're in fixed positions 2 meters apart. They're in fixed positions. That means that we know that when a force acts on these charges, if they're not in fixed positions, then these charges can move, right? So 1/10 of a second after the initial force acts, the force is going to be different because the distance is going to be different. Here they're telling me that they're in fixed positions, so that means they're not going to move. So that means that as long as we're going, the force is going to remain the same. The first question says, calculate the electrostatic force acting on the 2 charges. That's a really pretty straightforward one, and that wasn't the one that Silverose asked us to do, so we'll skip that one. Okay, if you have trouble with it, just F is equal to KQ1 Q2 over 2 squared, okay, and that's our answer. But B says the spheres are touched together and return to the original positions. What's the new electrostatic force on them? This is one of those questions where we've got 2 things going on here, right? We've got that charging thing, that charging by conduction. When they touch together, the charges want to balance out. And when they balance out, the force becomes different because the charges are now different. So let's figure out what the charges become. We've got 5 times 10 to the negative 5 coulombs plus 6 times 10 to the negative 5 coulombs. We're dealing with 2 charges that are both positively charged. Divide that by 2, we end up with 2 charges that are both 5.5 times 10 to the negative 5 coulombs. So now we're going to calculate the force using the new charges, which are both 5.5 times 10 to the negative 5. Now, I think we saw one of those maybe in our practice question set, or maybe it was our quiz number 9, I can't remember, where we had 3 charges. 1 touches 2, 2 touches 3. What's the force between 1 and 3, or something like that? Same deal here, except that we've only got 2 charges that we need to touch together. So we've got 8.99 times 10 to the 9 times 5.5 times 10 to the negative 5. Now I'm running out of space here, so what I'm going to do is just square that. Right? We've done that before, right? If the charges are the same, we can just square it if we want. It's the same thing. Divide it by my distance, which is 2.0. Common mistake here is forgetting to square that. So let's figure out what this is now. Let's say 8.99 times 10 to the 9 times, let's use my brackets here, 5.5 times 10 to the negative 5, and the bracket, and let's square that term. And then let's divide that by 2 squared. we end up getting 6.79 or 6.80, I guess it would be. Is that okay? All right, good. Let's move on to the last two questions we need to go over. Question number 9, two qualitative questions, two good conceptual qualitative questions here. Number 9 says a helium nucleus has a positive charge with a magnitude twice that of the negative charge on the electron. So let's draw this out. Not that we necessarily need to, but let's draw it out nonetheless. Helium nucleus has 2 protons, so that means the charge is 2 plus 2 elementary charge. Okay, not 2 electrons, 2 times the elementary charge. Okay, we have an electron orbiting around. Well, we actually have 2 electrons orbiting around, usually, at least in helium. But let's look at one of them specifically. We're going to say that the charge of that one electron is -1 times the elementary charge. Okay, and there is another electron orbiting around somewhere as well. Is the electrostatic force of attraction on an electron equal to the force acting on the nucleus? So let's first look at whether this is attractive or repulsive. Attractive or repulsive here? It's attractive, right? The electron's not going to orbit around the nucleus if it's not an attractive force. So it's an attractive force. The electron is pulled towards the nucleus, and the nucleus is pulled towards the electron. Which force is bigger? Which force is bigger? Now, why would the force on the electron be bigger? Because its charge is smaller? Because its mass is smaller? Anybody want to help justify that, or does anybody want to dispute that? The forces would be equal. Yeah. If I calculate the force between those two, it's KQ1, Q2 over R squared, right? Q1, Q2 over R squared. That force is that force. It's the same force acting on the nucleus as it is acting on the electron. And if object A applies a force on object B always applies an equal and opposite force on object A. They're going to be equal, right? Now, the effect of that force on the electron is much greater than the effect of that force on the nucleus. Can anybody tell me why that would be the case? You're not asked that in the question, but it's a good follow-up. Why is the effect greater on the electron? Even though the force is the same, the effect of the force isn't the same. Because it's its mass, right? The electron weighs, I don't know, about 1,000th or so of the mass of a nucleus or of a proton. So that means that the effect of that force, in other words, the acceleration, is going to be much, much less for the heavier object, like maybe 1,000th as much as it is going to be for the lighter object. Good. Number 10, last question here. It says electrical forces are so strong that the combined electrostatic forces of attraction acting on all the negative electrons and positive protons in your body could crush you to the thickness thinner than a piece of paper. Why don't you compress? Good. We got like charges in there as well, right? The protons and the electrons attract each other. Sure they do. But protons repel protons and electrons repel electrons. So you're going to get forces of repulsion going on in there as well. So at some point they reach a state of, what's that word again? Equilibrium, right? Where forces end up balancing. You get that attractive force that's trying to keep them all together, but you got repulsive forces of nuclei pushing on nuclei and electrons pushing on electrons and so on, so that they, at some level, they reach that state of equilibrium.